Okay, we're still on section 2.6, the second example. And again, it's always a good idea to draw a picture on word problems if possible. So I've got a rectangle in quadrant 1. Okay, here's quadrant 1. And the corner is on this graph. So this is a parabola that's been reflected and moved up by 25. Okay, so this is at 25. And because it's symmetrical, I know that this side is at 5, 0. This one is at negative 5, 0. And what do we know about a rectangle? One corner is on this parabola. Another is at the origin. A third is on the positive y-axis. Okay, if it's a rectangle, it's got to be right up here. And on the x. So here is my rectangle. This is just some point x and y. We don't know the specifics yet. Okay, express the area of a rectangle as a function of x. So I want something to look like a of x equals something. We know the area of a rectangle is the length times the width. So this is x, this is y, so it's x times y. And like example 1, if I want it as a function of x, I need to get this y out of here. I need to replace it with an x, or some expression with an x. We know from the problem that y equals 25 minus x squared, so I'm just going to replace that. So area of x as a function of x is x times 25 minus x squared. And let's go ahead and distribute that. So we have area as a function of x equals 25x minus x cubed. That is the answer to part A. We've now got the area of this rectangle expressed in terms of x. Part B, what is the domain? Okay, so what values can x have? Well, if we're in quadrant 1, that means I can't have a negative x value. And if I'm on this parabola, I can't get all the way up to 5. So I know that my x value cannot be 0, because if it's 0, we have no rectangle. So 0 is greater or is less than x, which is less than 5 is the maximum I can come over here and keep this rectangle with one corner on the parabola. So is less than 5. I can't have it equal 5 because, again, if it equals 5, there is no height to this whatsoever. Part C, graph it. So I want to graph this equation. So I'm going to put this in the calculator. And let's take a look. So I've got y equals 25x minus x cubed. And if I go to my graph, here's what I get. It came down, went up, and down. Well, great. Can't really see much there, but okay, I've got it. And it wants to know for what value of x is the area the largest. Okay, well, since the function comes down, goes up and back down, my local max is going to be somewhere here. So I'm going to have to play with my window. And something that's going to help me, I know it's between 0 and 5, so let's keep that in mind. And let's take a look at our table of values to see what y values we need to see. Let's see, we go up. Looks like 48 might be the highest. Oops, I wrote on the calculator. And so let's go to our window. We're only interested in x values between 0 and 5. So let's change from, we'll go to 0, 5. And y minimum, again, 0 is the minimum. Maximum, let's go up to at least 50, maybe 60, just so we can see it clearly. But use the table to help guide you on this. And that's what our graph looks like. It looks a little bit like a parabola. It has just been shifted over a little to its side. So here's my sketch of this. And I want to find the maximum area. So the maximum is going to be up here. So second trace, choose option 4 for maximum. And I need to have the cursor to the left of the maximum. And now I need to have it on the right of the maximum. Hit enter. And for guess, I'm not even going to bother. There is only one point in there, so I hit enter. It comes back and tells me, round it to 2 decimal places, 2.89, excuse me, round to 2 decimal places, is the x value. The y value here is 48.11. So when the x is 2.89, I get the maximum area, which is 48.11 units. I don't know what they are, but 48.11 square units. And that is example 2. Let's go ahead and see if we can get through example 3 now. Example 3, we've got 2 airplanes flying around. So my first airplane, I'm going to use different colors here so we can keep them, is flying south, which is negative y direction. It is going at 400 miles per hour, and it is 600 miles from where these 2 planes could hit each other or intersect if they were at the exact same height and if they got there at the same time. My second airplane is flying west. That means it's over here, going this direction. It is flying at 250 miles per hour, and it is a total of 400 miles from where they could intersect. Okay, and we want to create a function, build a model that expresses distance d between the planes as a function of time. Okay, so the distance between the airplanes is right here. That is my distance. And look at that, we've got a nice right triangle going on. Okay, so I'm interested in this leg and this leg. When time starts, I'm up here. If 1 hour went by, I'm traveling 400 miles, so I would travel down to approximately right here. So the distance I am now from the origin, or where they intersect, is going to be 600 minus 400. So let's figure out an expression for this leg. So it's going to be 600 minus our speed multiplied by, and it wants it in terms of t. So t is in hours, because we're going miles per hour. So after 1 hour, we'd have to subtract 400 miles from here. After 2 hours, it's already gone past that intersection point. So that is this leg right here. Okay, and Pythagorean theorem says that squared plus this leg squared will give me the distance squared. So this leg, we're going to do the same sort of thing. It's 400 miles, and we will have to, again, subtract however fast we're going. So 250 miles per hour multiplied by the time, and we'll have to square that. So that is my distance squared. Of course, we want just distance, so take the square root of all of this. 600 minus 400t squared plus 400 minus 250t, all of that squared. And this is a function of t, so I'll use my function notation over here on the left. Okay, there's my function notation. I've answered part A. I've created a model to express how far the airplanes are. Part B says let's go ahead and graph it. So we want to put this in our calculator or in Desmos, and here I've got it plugged in for us already. And I'm going to hit graph. And we don't see anything. So I've got to adjust my windows here. The first thing I know that is after 2 hours, these airplanes have passed each other. So my x values, I'm going to go to window. Minimum x is going to be 0, so time is 0. Maximum is going to be 2. For my y values, I'm going to be trying to find when are the planes closest to each other. So that's a minimum. So I'm going to my table, and I'm looking for what is the minimum value between 0 and 2. It looks like 223. So that's what I'm going to put in for my window for y. Y minimum is 0. Y maximum, let's put 250 is just a nice number and see if we see anything. Ah, look, and this is really what we're looking for. We wanted to have that minimum show up on our screen. So we've done good. Now let's just do second trace. We want the minimum, so option 3, to the left of that minimum. And again, it doesn't matter where on here you are, as long as it's to the left. Enter. And now we need to be to the right of that minimum. Enter, and we don't want to bother guessing. And it comes back and tells us that local minimum is at 1.53